Yeah, I'm going to follow up on what Nia was talking about, and I think the very important point is that solar activity is actually very important for changes in climate. And what we have been working on for now many years is actually trying to understand what the connection can be. And it's no surprise that I'm going to talk a little bit about clouds and the link to cosmic rays. Let me give you a sort of overview of what I'm going to talk about. I have two parts. The first is to give you a background of why I think cosmic rays are important and how they link to cloud. We have some experimental evidence, we have observational evidence, and I will talk about what can the link be between ionization in the atmosphere and then the formation of clouds. The last part will actually be on a field that was initiated by Nia. It has to do with changes in climate over millions of years. It's very interesting because it's completely independent of solar activity. Here you see more or less the idea which Nia also was presenting, that we have cosmic rays, which are particles that comes from space, and they are mainly produced in stellar processes where we have supernovas and they make a shock front and that accelerate particles to very, very high energies. And these particles, they shower in over the Earth. And there are two things that can modulate the cosmic rays. One is solar activity. It's on the order of 10%. And the other, which I'm going to talk about in the last part of the talk, is that you can have changes on the order of 100%. So when I started this, I knew that people have been finding correlations between solar activity and climate. And the question I asked me was, if it's going to work, it might actually be clouds that are affected by cosmic rays. That was sort of the fundamental idea. And when I found data, here you see data from '83 until 2005. The blue curve is actually from a satellite data set of low clouds, and you see this nice correlation. The red curve here is the changes in cosmic rays over the same period. So it gave an impression that maybe there's something interesting going on. But of course, this is just a correlation, so there's no guarantee that there is a physical mechanism. And at the time when we presented this, many people were saying that there's no known mechanism, so we actually don't believe that this can be right. It could be some accidental correlation. And I should also say that the changes in cloud cover observed from satellites is very, very difficult. It's very, very difficult to maintain a calibrated system. So you might end up where the correlation actually breaks down and you cannot be sure what is the cause of it. So there's no guarantee that this is necessarily, a causality that we have between the two curves. As Nia showed, the effect of solar activity over 11 years is of the order of 1 to 1.5 watt per square meter, so over the 11 years. And the changes I just show you in cloud cover, they are actually of the order that fits within this picture. So it could be that the clouds are the amplifying mechanism that makes solar activity so important in our climate. So the obvious question is, how do cosmic rays affect climate? And the idea is that, you have to understand how clouds are formed. And in order to have a cloud, you need what we call cloud condensation nuclei. These are very small aerosol particles. They have a certain size on the order of 50 to 100 nanometer. And at that size, water vapor can condense on them and they can become cloud droplets. The fundamental question is then, how are these small cloud condensation nuclei formed? And it turns out that a large fraction of the cloud condensation nuclei are actually formed directly in the atmosphere from gases. So you have molecules in a gas, and then they can stick together and make a small cluster. And this cluster might be stable, and you have a small aerosol, and then subsequently it grows by condensing more gas, and finally it becomes a cloud condensation, it becomes a cloud droplet. So the idea that we had was that this ionization from cosmic rays that is happening in the atmosphere all the time, it actually promotes the stability and the formation of these small particles. That was the fundamental idea. Now, here you actually see a very good example of what happens if you change the number of aerosols that goes into the atmosphere. Here you have a region over the oceans with low clouds, and these stripes here are actually ship tracks. So what is happening is that a ship from the engine is pumping out a lot of aerosols. These aerosols goes into the clouds, and you all of a sudden get condensation of water vapor, but you see that you change the microphysics along the track of the ship. And the idea is that if you can do this systematically, I mean, if solar activity is capable of changing the number of aerosols or the aerosol properties, it will be a very effective way of changing the radiative properties of the Earth, of clouds, and so on. So that was the idea, and the initial thing we did was that we could test these things experimentally. We could test whether small ions actually promote the formation of small aerosols, okay? And this has actually been measured, and I think this is the measurements we did. This is from 2006 when we first published it. It came out 2007. Nonetheless, what you have along this axis is something that corresponds to the ionization or the cosmic rays. And when you increase the cosmic rays, you increase the number of, or the formation of small particles in our experimental chamber. And in 2011, the Cloud project actually came up with the same or similar results, showing that when you increase the ionization in the chamber, you are producing small aerosols. So we have a production of aerosols. So that, you can say that was very supportive of the theory, but it is extremely important that these small particles, that they grow to cloud condensation nuclei, and if they don't do that, they will not affect climate. And it turns out that there was a number of groups that put this mechanism into large models, climate models, and tested what happened if they increased the number of small cloud condensation nuclei as the solar activity changed. So they are sort of testing the idea, and it turns out in all of these simulations, even though they put in extra of these small particles, more or less none of them grow to cloud condensation nuclei. And that was seen as a fundamental problem for the whole idea. It was said many places that that was the end of this idea. But fortunately, we can also test it in the laboratory. So the important thing is that modeling says no to this effect on ions on cloud condensation nuclei, and therefore there's no link, or it's not important. But we could actually address it in our laboratory. So what we did was the following. We had our cloud chamber here. We could shine UV light, which corresponds to the effect of the sun. And then we can put in various gases. And when we had this light, we are producing small aerosols all the time. Then we can add ionization from these radioactive sources, which is like turning up and down the cosmic rays. And then we can measure what is going on. And this is a picture of the chamber. It's about 8 cubic meters large. You can see the radioactive sources here and here. Okay, but here you see a typical experiment where we are shining light in on this part of the chamber, producing small aerosols, and they are growing, and we have the size of the particles going up this way, and this is the number of particles, and they go into a steady state. And then we can sort of add some extra particles by different methods. And then we can see what is the fate of having additional small particles. Will they grow to cloud condensation nuclei? That is the fundamental question. And the first experiment we did was to add neutral particles to our chamber, very small particles on the order of 3 to 5 nanometers. And here you see the result. Here you have the size. This is about 10 nanometers and this is 70 nanometers. At this size they are cloud condensation nuclei, so they are large enough. And what we do is we increase the number of particles with about 50%. And then you see as they grow, fewer and fewer of them actually makes it to cloud condensation nuclei. So when we add neutral aerosols and we are not using cosmic rays, the result is in complete agreement with the numerical modeling. And the reason is that when we put in more particles, we have more particles competing for the same gas that they have to grow from, and then they grow slower, and there's a larger chance that they get lost by some process. But then look what happens if we do it with cosmic rays. If we add cosmic rays to the chamber, we produce about 15% more small particles, but notice that nearly all of them grow to cloud condensation nuclei. And that is in complete contradiction of all these modeling results. So something is going on which is not in any of the physics of all these models. And this could very well be the reason why this mechanism actually might work in the real world. However, people were telling us that maybe we have a mechanism that works in our laboratory, but if you go out to the real atmosphere, it might not work. There are so many other processes that are producing cloud condensation nuclei, so therefore it need not to be important. There are so many other processes, so it will just drown. So what we did was to look at what we called natural experiments that the sun is providing us. We have these coronal mass ejections where you have a large piece of plasma that comes out. If you imagine the sun here and you have this plasma, if it hits, if the Earth is here, for instance, and it hits the right way, then there is a sudden drop in the cosmic rays. That means that when these effects are happening, we can use it to test whether there is an effect on clouds and other parameters relevant for these ideas. And here you see the result. This is the red curve here is the change in cosmic rays because of these events on the sun. These are the 5 strongest events over a period of 20 years. What you have here is day 0. That is when we have a minimum in the cosmic rays, and then we have 20 days after the event and 15 days before. And then we look, for instance, at the liquid water that we have in clouds. This is liquid water in the clouds over the oceans. And you see that there is a distinct drop in the liquid water following the events in the cosmic rays. And this is on the order of 6% change in the liquid water, so it's actually quite large. And it's not just this satellite data set that shows this. We can take other satellite data set which has other temporal, they covered different temporal periods, and still we see these drops following the effect of the cosmic rays. And finally, we also see the effect in the aerosols, suggesting that we are observing more or less the whole chain from solar activity to cosmic rays to aerosols to clouds. So this is a strong support of the idea that there could be such a connection. Okay, so we have a mechanism, and it looks as if it is working in the real atmosphere. What I want to show you now is when we go to the very long time scales. I just told you that when we look at longer time scales, we can have variations on the order of 100%, which are completely independent from solar activity. And if this mechanism is something that has been operating for, during all times, we would expect, or we could hope for, to find correlations even on very long time scales, which would be an independent support for the idea. Now, when we look at these very long time scales, and this is the work of Nir, that if you imagine that the solar system is moving around, we go in and out of regions where we have these red dots, which is supposed to be supernovas going off. So at some periods we are between these spiral arms, and sometimes we are in a spiral arm, and that should give a large change in the amount of cosmic rays during this journey. And I should say that the journey takes about 240 million years just to go around once, so it's quite long. Here you see Nir's estimate of how the cosmic rays has been varying over this period of time, and this is actually related to various spiral arms. You see them here. And if you now compare it with the work of Jan Weiser, you see where this is supposed to be the red curve, the temperature of the oceans, in the tropical oceans over the last 500 million years. You see this very nice correlation. So that was sort of the start of these independent check that there's also a correlation even on these very long time scales. Now, the support for this model, there are various support. One is that we see something which is similar to 140 million year period in climate. Nir has also shown that there seems to be 140 million year in iron meteorites, and that actually has to do with exposure to galactic cosmic rays. So this is also in support that the interstellar environment is changing with this period. I want to show you the last part here, some of the work that I have done, which has to do with open cluster formation and supernovas. And what I want to do is to try to reconstruct the number of supernovas that went off in the solar neighborhood over the last 500 million years. So to that end, I'm going to use what we call open stellar clusters, and there's one open stellar clusters that nearly all people know, which is the Pleiades. It's about 200 million years old. It's about 1,000 stars. And the thing is that these stars, it's a group of stars that are bound by gravity, and they're all formed from some molecular gas cloud that collapses, and you make a lot of stars which are born at the same time, all in a group. So here you see this is a sort of a bird's eye view of our Milky Way. This is the solar system. This is about 3,000 light years. And each dot is an open stellar cluster. This is the Pleiades that is right here. So that is fairly close to our solar system. But what is interesting is that most of these dots are blue, which means that they are quite young. And I can make an age distribution of all these open clusters, and it looks something like this. So here you see this is present, and this is 500 million years ago. And you see there are many more young clusters. And then as a function of time, as we go further back, we have fewer and fewer clusters. And the question is whether this curve actually says something about the formation of star formation in the solar neighborhood. And I want to make the case that it actually do. So the idea is to use this information. I can take what we call the star formation over this period. It's actually the cluster formation. And then when I produce a number of clusters or stars, then a certain fraction of them will explode as a function of time. Within 40 million years, all of them will be more or less exploded. And if I combine these two things, I get the supernova rate. And that's exactly what I want. So I want to see how did the supernovas change over the last 500 million years. And the supernovas, of course, is a measure for the galactic cosmic rays in the solar neighborhood. Okay? And this is the result. So here you see, you can more or less see these wavy form, which has to do our patches through spiral arms. And an obvious question is, of course, whether this is a real curve, or is it just noise that I have amplified? Is it a real signal? And we can actually try to estimate it in a different way. First of all, let me just show you that if I take different open cluster catalogs, I get more or less the same results. So it's not really dependent on one particular data set. But I can actually try to justify it by looking at molecular gas distribution in the galaxy, because this molecular gas, it says something about if you have a high gas density, it says something whether you will form stars, and then subsequently whether they will become supernovas. And if you use this information, here you have one example. This is then the gas distribution in the Milky Way, or an attempt to get it, where you have the solar system here, you have the galactic center, and you have the opposite part here. It's actually very difficult to get the information in this part, but that will be relevant in just a second. But it means that I have two ways of producing something which is related to the star formation, either from the open clusters or from the gas concentration. And when I compare the two, the red curve is from the open stellar clusters, and the solid line is from the gas. And you see, except for this region here where there are some problems, it actually seems to reflect some of the same changes. So this is my justification that maybe it's not completely wrong to say that the cosmic ray history has looked something like this. Okay? So when we have the cosmic ray history, we want to compare it what happened on Earth during this period of time. And this is where geology comes into place. Here you see some sedimentary mountains. All these layers has to do with ancient seabeds. And from this you can, from isotopes, carbon-13, oxygen-18, you can get information on the timeline or dating. You can get fossils, so you say something about the evolution. You can say something about the sea levels, glaciations, and therefore, of course, also on climate. So you can get a lot of information that you can compare with. Let me. This is just to show you the part of time that we are looking at. This is more or less the last 500 million years. And of course, the continents has been moving around like crazy over 500 million years. And life has moved from the oceans to land, and many things has happened. So therefore, it would be quite remarkable if there was something, common that comes from the outside that actually can explain some of the things that has happened over this period of time. And this is exactly what I want to show you now, that there are these correlations. Now, the first thing is to compare sort of in a crude way with climate. And what I have here is, an attempt to make a bar where the blue is a cold ocean, the red is warm. This hatch is when we have glaciations. And if you look now, you see we have glaciations here in this period. Then it's fairly low, and we don't really have glaciations. We have some periods with some cold. But then we get glaciations again. It fits fairly beautiful with the increase here. Then you see here we have a cold ocean and some glaciations. Then again we have cold ocean, glaciations, and so forth. Now this is of course very crude, but we can do it slightly better. And this is actually the work also of Jan Weiser and his colleagues, where they use these bradiopods as to say something about the temperature at the time when these animals lived. By looking at the oxygen 18 in these shells, it says something about the temperature of the ocean when it lived. And these animals have been living, for a period over more than 500 million years. So you can actually get a curve of temperature over quite a long period. And here I show you 200 million years. Now, the red curve is the change in cosmic rays, or the supernova rate. And all these dots are from these shells. And you see that there are very nice correlations, especially if we go to the more recent part. Here you have the glaciation of Antarctica, then it heated up a little bit, and then it reglaciated again. And it fits fairly nicely with these changes. So, another thing I want to mention, because, when I show this figure here, I'm showing you just the level of supernovas over this period. But in reality, supernovas are, of course, more or less discrete events that are happening in time and space in the solar neighborhood. And that means that we will have fluctuations in the cosmic rays. And here you see, an attempt to make a time series of how large the fluctuations are. Now, the size of the fluctuations depends on certain parameters, but nonetheless, you will actually expect on these timescales to have a fairly fluctuating system with the cosmic rays. So, what I've been showing you up until this point is sort of average features. Now, if we start looking at sea levels, this is over the last 50 million years, and this blue curve is actually changes in sea level. You see the sea level here, and the changes is actually on the order of 100 meters or more. But you see that there are these spikes in the sea levels as a function of time. And the question is whether, when I show the modeling of the cosmic rays over this period, whether this is actually something that could be the cause of these sudden changes in sea level over this period. The red curve is the average change in cosmic rays or supernovas over this period of time. Now we come to the last two graphs. And I want to show you that we have been talking about that there seems to be a correlation with climate on these timescales. Now I want to show you that it's not just climate, but it's actually life itself on Earth that seems to be very much affected by the supernovas in the neighborhood. of our solar system. Now we know, of course, that the solar energy, or all the energy for life, comes from the sun. So we have a life in the oceans. We can have a large bioproduction, but in order to get this bioproduction, you have to get nutrients into the oceans. And these nutrients are like phosphor or iron or nitrogen. It has to be either blown or run off, and that sort of supports the life. When life dies, it actually sinks down into the water column, and let me see. And it's very important, of course, that we have mixing of some kind so we can support a large biomass. But what is important is that when we support life, it's of course carbon that is the most important part of, this is the building block of all life. And it turns out that life prefer to take the light form of carbon, that is carbon-12, instead of carbon-13. So if you have a large biomass, then a lot of the carbon-12 is locked into the life, or into the biomass. And that means that when we have inorganic carbon sediments, when we have changes in the biomass, and also, so you can see it this way, that when you have a change in the biomass, you actually get a change in the carbon-13 in the sediments that you can now drill out. So if you take out some of these sediments today and you measure the changes in carbon-13, it says something about what happened with the biological system as a function of time. And here, now I want to compare these two, and I will show you that there is a remarkable correlation. So this is the change in cosmic rays, or the supernovas over this period of time. And if I compare with the carbon-13, how that has changed, it looks something like this. And you see that, if I made an average of it, it will actually follow this curve very, very beautifully over this period of time. And it's quite remarkable that the correlations are so good. So let me conclude. We see that variations in cosmic rays seems to be associated with changes in the Earth's climate, and we have very strong empirical evidence. And the evidence also suggests that clouds are very important. It could actually be the link. The mechanism, which is of course the basic of understanding, why there is these connections. I think we are making progress, and it involves the ionization and the formation of aerosols in the Earth's atmosphere. And it shouldn't be necessary to say that if you change clouds, then you can change the energy budget of the Earth. And I think that with this cosmic ray climate link, I think that it can have very large implications for our understanding of, not just the history of the Earth, but also the history and the conditions for how life has evolved as a function of time. Thank you very much.